Hey there, welcome to the Electronics Lab. In this video, I'm going to try to fly through 5 example problems where I need to calculate the voltage, current, and power in a circuit where I have a combination of parallel and series resistors. So let's not waste any time and jump into solving these problems. All right, here's the first circuit, and we can see we have a combination of parallel resistors in series with a single resistor here. And so the process we want to do is break this down into a circuit that has one equivalent resistance and then build it back up, calculating the voltages across and currents through those resistors as we build the circuit up. So this circuit, what I see here, I've got R2 in parallel with R3. And the calculation for that will be the inverse of 1 over 100 plus 1 over 400. And that works out to 80 ohms. Now, I'm not going to redraw the circuit yet. I'm going to combine it with this R1, this 100 ohm R1. 100 ohms plus 80 ohms gives me 180 ohms. So the equivalent resistance then for the entire circuit, I'll have a 24 volt source and a single resistance with a value of 180 ohms. Now that I know this, I can figure out the total current. Using Ohm's law, 24 over 180 gives me 0.133 amps. Okay, that 0.133 amps is coming from the source and is going through R1. So IR1 will also be 0.133 amps. Fill in the table over here with what I already know. And since I now know the current through R1, I can calculate the voltage drop across it. VR1 will be, and from Kirchoff's voltage law, I know that the voltage across R2 and R3 will be equal, and also that it will be 24 minus the drop across the R1, so 10.7 volts. And the current through R2 and R3, they're going to be different. It's going to be the split of 0.133 amps. So some of that 0.133 will go through R2 and some will go through R3, and we can use Ohm's law to figure out how much. And through R3. And finally, I need to calculate the power. Power is equal to voltage times current. I know the voltages across and the current through each one of the components, so those will be simple calculations. I won't write out PR3 calculation. Again, it will be the current times the voltage, and it works out to 1.14 watts. The total power will be power dissipated by resistor 1 plus the power dissipated by resistor 2 plus the power dissipated by resistor 3, and that works out to 3.192 watts. Let's just go 3.19 watts. I could have also got this by calculating the total current, 0.133 times 24 volts. And that's it. Let me just fill in the rest of the table here. All right, here's problem number 2, and I have filled in the table with the values that I know from looking at the circuit. This one's a little bit different because I don't know what the source voltage is. I do know what the current through R1 is, and I should be able to figure out all of the rest of the values. The very first thing that I see is since I have 1 amp going through a 16 ohm resistor, I know what the voltage across R1 is. It will be that current times the resistance, 1 amp times 16 ohms. That gives me 16 volts. And look, R1 and the source voltage are in parallel with each other, so Vs will also be 16 volts. What should I do next? Well, I have 16 volts across these two resistors, and those two resistors are in series, so I can redraw the circuit to look like this. This equivalent resistance will be R2 plus R3, 8 ohms plus 4 ohms, so that will be 12 ohms. So I can now figure out the current through R2 and R3 will be the current in this branch, which is the same as the current in this branch, and that will be 16 volts over 12 ohms, which gives me 1.33 amps. And now with that current going through R2 and R3, I can figure out the voltage across R2 and then the voltage across R3. V equals I times R. I have 1.33 amps times 8 ohms, and that gives me 10.64 volts. And VR3 could be calculated in the same way. The last thing to calculate is the power. And since I know the voltage across, currents through, and the resistances of all of these components, I can use any of my power equations to calculate the power. So let's do it in a little different way for each one. Okay, so for power for R1, let's do I squared R. So that will be 16 watts. For R2, let's do V squared over R. That works out to 14.15 watts. And for R3, let's go back to Old Faithful, V times R. Or sorry, V times I. And the total power, let's also use V times I. Well, actually, I haven't calculated the total current yet, have I? Let's do that. The total current will be the 1 amp that's going through R1 and the 1.33 amps going through R2. So that will be 2.33 amps. And so the power total, 37.28 watts. I'm just going to write it in here. 37.28. One thing I didn't calculate because I didn't actually need it for any of the calculations for the circuit so far is the total resistance. The total resistance seen by the source will be the 16 ohms in parallel with 12. So that will be the inverse of 1 over 16 plus 1 over 12. And that's 6.86 ohms. All right, next circuit, we have a 40 volt source, R1 of 10 ohms, R2 of 10 ohms, and R3 of 10 ohms. But let's take a look at what's really going on in the circuit here. We have 40 volts applied across R1, and then we have R2, and that's just hanging to a connection over here that I've labeled A, and R3, that's also just hanging over to a connection that I've got labeled here B. There is no connection between R2 and R3 here, and therefore there's actually going to be no circuit, no completed circuit here. Well, it's an open circuit, so there's no current going through R2 or through R3. So right away, I've got IR2 equals IR3, which equals 0. And since there's no current going through those resistors, VR2 is equal to VR3, which is also equal to 0. 0 volts there and 0 amps for the current. Over here in R1, well, the voltage across R1 is everything from the source. So VR, that should have been 1. VR1 is 40 volts. And I can use an application of Ohm's law here to figure out what the current through R1 is. It's that 40 volts across the 10 ohm resistor gives me 4 amps. Now, it's not in the table down here, but the voltage between points A and B is an interesting one. Because there's no current going through R2 and no current going through R3, point A voltage is at the same potential as the point over here at the top of R1, and the voltage at B is the same over here at the bottom of R1. So basically, VAB is going to be the same as the voltage across R1. So VAB is also 40 volts. Now let's fill in the table with everything that I have so far. So the only thing I don't have is the power. Well, power dissipated by R1 will be that 40 volts times the 4 amps going through it, 160 watts. Power dissipated by R2 will be the same as the power dissipated by R3. Remember, both those voltages and both those currents are 0 watts. And the total power, so this is the power put out by the source, that will also be 160 watts because that's the power that's dissipated by R1, the only resistor that's dissipating power in the circuit. All right, well, it looks like here we have the most complicated circuit that we've seen so far. So I'm going to go through this very systematically and break down the circuit, reduce the circuit to a single equivalent resistance, and then calculate the total current that would be output by the 80 volt source, and then build the circuit back up to calculate the voltages across and current through all of the different devices here. So the first thing I'm going to do is actually redraw the circuit in a more standard form where I have the voltage source over here on the left-hand side. And R3, which is right here now, is connected to R2 and then to R1 and then back to the 80 volt source. So I can draw that in parallel on this side of the voltage source instead of on the left side. And R4 was also connected in parallel with the combination of the 80 volt source and R3. Okay, now I can start combining resistors to work towards a circuit where I have only one equivalent resistor in the circuit. I see here R1 and R2 are in series, so I'm going to combine those to give me the R1 plus R2. And I've added R1 plus R2, so I'm going to actually put it in the table here. And next I can combine this R1 plus R2, which is in parallel with R4. So that total resistance will be the inverse of 1 over 5K plus 1 over 7K. Instead of writing out R1 plus R2 in parallel with R4, I'm just going to call this R5. And the value of R5 is 2.9K. And one last step to do here, combine R3 and R5, or at least one last step in figuring out the total equivalent resistance. And I'm just going to call this RT for total. And so that'll be the 2.9K plus 1.5K. Okay, now starting from this final circuit I've got here, I can figure out the total current. Total current will be 80 volts over that 4.4K total equivalent resistance. And that works out to 18.2 milliamps. Now, if I go back a step here to this circuit, that 18.2 milliamps is going through R3 and R5. So the current through R3 is 18.2 milliamps, and then I can figure out the voltage across it. So VR3 is 27.3 volts. And VR5, well, I can calculate VR5 a couple of ways. I am going to go using Kirchoff's voltage law. So 80 volts from the source minus 27.3 volts across VR3 is going to be what's left for VR5. And that's 52.7 volts. Okay, I'm going to start filling in the table here. A lot of time passed here. All right, going back a step, converting R5 back into R1 plus R2 in parallel with R4, the voltage across this part of the circuit is that 52.7 that I just calculated. So if I have 52.7 volts across R4, I can calculate IR4. And that equals the value here that I'm going to put in the table. Voltage of R4, 52.7. R1 plus R2, also 52.7. And now I can calculate the current. 52.7 over 5 kiloohms. And I'll write the value down here in the table. So the current through R1 and R2 is 0.0105 amps. And now I can go back one more step to this circuit. If the current through the equivalent R1 plus R2 is 10.5 milliamps, then the current through R1 and the current through R2 will also be 10.5 milliamps. I'm not even going to do that calculation on the paper because it's just equal. What I will do for calculations, though, is the voltage across R1. That will be the current through it, that 0.0105 amps times the value of R2, which is 2000. That works out to 21 volts. And VR2, similar calculation, but it's a 3 kilo ohm resistor. So that 0.0105 amps times 3000, 31.5 volts. And power is equal to voltage times current. All right, only one circuit to go. In real time, I'm at 40 minutes. Okay, here's the one final circuit. And this one looks a lot different than the circuits that you've seen in the past because I have added a new device which you may or may not have seen. This is a BJT, or a bipolar junction transistor. And I'm not going to teach you anything about how it works except tell you a couple of things. And this is a good precursor for any electronics courses that may be coming up for you. We don't need to know a lot about the BJT to do the analysis on the circuit to find the voltages across and the currents through these circuits. A couple of things that we do need to know. The way that the circuit works is well, at least in this particular case, for this particular BJT, the current IC, which is going here, and C stands for collector, is equal to 100 times IB, which is the current here, and B stands for base. That's just a property of the transistor. Current coming into the base here will drive the collector current and make it equal to 100 times that base current. The other piece of information that we need to know here is there is a fixed voltage drop between the base and this junction of the transistor over here called the emitter. That's the VBE voltage, and that's equal to 0.7 volts. So using these two pieces of information, we will be able to figure out the voltages across all of those resistors as well as the currents through them. And the way that we can do that is we can break the circuit down into a couple of different pieces and apply Kirchoff's voltage law, Kirchoff's current law, as well as Ohm's law. So what I'm going to do is just look at this part of the circuit here. And that will give me one KVL loop. Instead of drawing the BJT, we can just consider this a black box. Doesn't really matter what it is. We just know a couple of rules about the way this black box works. The voltage between that point and that point is fixed at 0.7. And we have an additional current coming in here that's kind of changing the way that it works. So this is IC coming in, and then we have IE coming out down here. And we also have another IB coming in. So remember, this is a 200 kilo ohm resistor, and this is a 900 ohm resistor. Over here, we have 5 volts. So going around the loop, let's say we're starting at here. Here's our reference point. We go up 5 volts. So let's write out that KVL equation. We go up 5 volts. And then we drop some amount across that 200K resistor, and that's going to be equal to IB times 200,000. And then we drop 0.7 volts. And then we drop some amount across this 900 ohm resistor. So that's going to be IE times 900. And that brings us down to 0. Now, we know that IC is equal to 100 IB. And look at IE. IE will be the sum of IB plus IC. We've got an application of Kirchoff's current law right here. 2 currents into this junction, IB and IC, and 1 current out. So IE is equal to IC plus IB. But remember, IC is 100 IB. So this will be 100 IB plus IB. And that gives me IE as 101 IB. So I can plug that number into the equation here. I have 5 volts minus, let's just rearrange this so it's 200,000 IB, minus 0.7 volts minus 900 IE, but that's 900 times 101 IB. So that's 90,900 IB equals 0. Now look at this equation. There's only one thing in here that we don't know. Forgot the B there. And that's IB. So I can solve for IB. Isolate the IB values on one side of the equation, and I get 290,900 IB is equal to, well, 5 minus 0.7, so 4.3. So that means IB is 4.3 over 290,900. And that works out to 1.48 times 10 to the minus 5 amps. Okay, so we've got an IB value. We could easily calculate the voltage across the 200K resistor. Just multiply that IB times 200,000. But let's go to this loop to figure out what the voltage across the transistor is here. And let's call that VCE. So again, if we got a black box. We've got an IB coming into it. We have an IE coming out of it. We know that, well, we don't know the voltage of it yet. It's VCE, and we want to know what that VCE is. Up here, we have another resistor, and then we have an 18-volt source. Okay, well, pretty easy to figure out what the voltage across the collector and emitter is because we know IC. Well, we don't know it quite yet, but we do know that it's equal to 100 IB. So that's going to be 100 times 1.48 times 10 to the minus 5. That means it's 1.48 times 10 to the minus 3 amps. So 1.48 milliamps. And IE, that's this current here, is just about the same. It's 101 times 1.48 times 10 to the minus 5. So IE is 1.49 times 10 to the minus 3, or 1.49 milliamps. Okay, well, in this loop, let's see, we have an 18-volt source. So we're starting here in the corner. We've got an 18-volt source. We're going up 18. Let's write out the equation for it. Minus IC times 3,000 for the voltage drop across that resistor. Minus VCE, minus the voltage drop across the resistor at the emitter. So that's going to be IE times 3,000. And that brings us back to the beginning again, back to 0. So the only thing in this equation that we don't know is VCE, because we can plug in this value for IC and this 1.49 times 10 to the minus 3 for IE, and we get VCE is equal to 11.78 volts. And that's as far as I'm going to take it for this circuit. I'm not going to calculate the voltage across and the power dissipated by all those resistors, because when you're doing a transistor analysis, you want to figure out what are the characteristics, what state is the transistor in. And that state consists of the VCE value and the IC value, which we've just calculated. So we know what the operating point of that transistor is. And that's the important part of a BJT circuit. Not that you need to know it at this point, but it's a nice little precursor to what may be coming up in a future or even a current electronics course that you may be taking. So the analysis, at least the DC voltage analysis of a BJT, requires all those basic rules that we need with electrical circuits. We need to know Ohm's law, we need to know Kirchoff's voltage law, we need to know Kirchoff's current law. Those three laws combined with a couple of things about transistors, one, that IC is equal to some value times IB, in this case is 100, and two, there's 0.7 volts between the base and the emitter, 0.7 volt drop, and three, it's got three terminals, and there's current going into the base, current going into the collector, and then current coming out of the emitter. So we can apply Kirchoff's current law there. And that's it. I got through my 5 circuits in real time. That was 50 minutes, 48 minutes and 30 seconds. Let's see how we can do with editing. How far can we bring this down? Can we get it down to 5 minutes? All right, well, take all of this information, take all of this practice that I've given you, and go forth and complete your own assignments. Thanks for watching. See you next time. Hey, and if you did like the video, please like it with a button, not just in your mind and heart. And subscribe. Thanks.